Hello, I'm Miss Ginsburg with KnowAtom, and today we're going to be reading Waves and Information Transfer. This is a lab manual in Unit 9. Section 1, Detecting Earthquakes, a surprise in earthquake research. A group of scientists in Southern California spent 6 months in 2011 listening to vibrations deep within the planet. They focused on a region in Southern California around the Newport-Inglewood Fault. This fault stretches nearly 80 kilometers or 50 miles from Culver City to Newport Beach. The scientists made a surprising discovery. They learned that small earthquakes occur much deeper in Earth's interior than they thought possible. Their findings will require additional research to help them understand how this is possible. This is a wide open question that we don't have a good answer to, study co-author Asaf Inbal told Science News in 2016. The scientists were surprised because of the properties of Earth's 4 internal layers. The inner core is Earth's hottest layer and is made up of a mixture of solid iron and nickel. It is surrounded by an outer core that is made up of a less dense mixture of liquid nickel and iron. Surrounding the inner and outer core is the mantle, which is mostly molten, semi-solid rock called magma. The mantle is in constant motion, powered by the transfer of energy between Earth's warmer and cooler materials. Earth's crust is the hard rock layer of the planet that supports the continents and oceans. The crust is Earth's thinnest and coolest layer. Here's Earth's 4 layers: the crust, the mantle, the outer core, and inner core. Tectonic plates and earthquakes. Earth's surface is fragmented into drifting slabs of solid rock called tectonic plates. As magma moves beneath the crust, it pushes the tectonic plates toward or away from each other. A fault is a break in the rock where rocks on either side have moved past one another. Faults often occur where Earth's tectonic plates meet. When two tectonic plates suddenly slip past one another, there is a sudden release of energy that causes the ground to shake, producing earthquakes. According to some estimates, 1.3 million earthquakes occur every year. Most earthquakes are so small that we do not even feel them. Occasionally, however, the energy released by an earthquake can dramatically shake the ground. This can cause buildings to collapse, mudslides to happen, and tsunamis to form. Energy of an earthquake. All earthquakes occur as energy transforms from potential to kinetic energy. As the plates move, they release kinetic energy. The edges around the tectonic plates are jagged, causing them to get stuck on other plates as they move. Because magma is constantly moving below them, the rest of the plate tries to keep moving. As a result, the energy that would normally cause the plates to slide past one another transforms into stored elastic energy. When the forces of the moving plates finally causes the jagged areas of the plates to separate, huge amounts of kinetic energy are released. The earthquakes recorded by Asaf and his team were more than 30 kilometers or 18 miles deep within Earth's upper mantle. This was surprising to the scientists because the rocks here are so hot they should flow like hard honey when under stress, rather than accumulate stored energy. Earth's surface is broken into tectonic plates. Waves transfer energy. Asaf is a seismologist. Seismology is the study of earthquakes and seismic waves that move through and around Earth. Seismic waves are the waves of energy caused by the sudden breaking of rock within Earth or an explosion. All waves are disturbances that travel through space and/or matter, transferring energy as they move. Seismic waves are similar to sound waves and water waves because they are mechanical waves, which means they are caused by vibrations in matter. As mechanical waves travel through a medium, they cause molecules within the matter to bump into each other. As this happens, energy transfers from one molecule to the next. It is important to note that waves don't carry matter. After the energy moves through, each molecule will return to its original position. Seismic waves from an earthquake. The point within Earth where the rocks start to fracture or break in an earthquake is called the focus. This is the source of the initial disturbance. The energy released travels out in all directions through seismic waves, much like ripples traveling outward when you drop a pebble in a pond. The epicenter is the location on Earth's surface where the earthquake starts. Earthquakes cause seismic waves that travel through Earth's interior. Types of waves. There are two categories of seismic waves that transfer energy: body waves, which travel within Earth's interior, and surface waves, which travel at or near Earth's outer surface. There are two main types of body waves: primary waves and secondary waves. P waves are a kind of wave called a longitudinal wave. This is because the disturbance moves parallel to the direction of the wave itself. If the wave moves from left to right, the disturbance also moves from left to right. As longitudinal waves move through matter, molecules press together. This is called compression. When this happens, the molecules on either side of the compression spread out. This is called rarefaction. Kinds of longitudinal waves. P waves, or primary waves, are longitudinal because they push and pull the rock they move through. This causes the vibrating molecule to move in the same direction as the wave. This is similar to the movement of sound waves, which are also longitudinal waves. As they move through a medium, the molecules of the medium collide with one another in the same direction the sound wave is moving. This is a P wave. S waves are a kind of wave called a transverse wave. In these waves, the disturbance moves perpendicular to the direction of the wave itself. In other words, if the wave moves from left to right, the disturbance moves up and down. S-wave move molecules up and down perpendicular to the direction the wave is traveling. When a crowd of people in a stadium do the wave, they are modeling a transverse wave. The individual people move up and down while the wave moves from left to right or right to left. This is also an example of how waves move energy, not matter. After the disturbance passes through, the people go back to where they were before the wave moved through. So here's a diagram of an S wave. And here's a transverse wave. Wave patterns. All waves represent repeating patterns. This can be understood by thinking about the anatomy of a simple wave. The wavelength is the distance spanned by one cycle of the motion of the wave. In transverse waves, it is measured as the distance between two crests, the top of the wave, or two troughs, the bottom of the wave. In longitudinal waves, it is measured as the distance between two compressions, points where the molecules are pressed together, or rarefactions, points where the molecules spread out. Amplitude and frequency. The amplitude is a measure of the wave's displacement from its resting position. For example, a water wave's amplitude is its height above the water's surface. In a longitudinal wave, the amplitude is the amount of compression that occurs as it moves through the medium. In all mechanical waves, the amplitude is proportional to the amount of energy carried. If the amplitude of a mechanical wave doubles, the wave will have 4 times as much energy. The frequency of a wave is the number of waves that pass a set point in a given amount of time. A wave with a greater frequency transfers more energy in a given amount of time than a wave with a lower frequency if the amplitude of both waves are the same. Here's a diagram of a longitudinal sound wave and of a transverse wave. How seismic waves travel. Body waves from an earthquake have a higher frequency than surface waves, and they arrive at a seismograph before surface waves. Seismographs are devices with a sensor to detect the ground's motion along with a recording system that graphs the seismic wave patterns. P waves are the fastest kind of seismic waves, so they are first to reach a seismograph. They can travel through solids and liquids. They often travel upward through Earth's layers, shaking the ground in a vertical motion. S waves are slower than P waves, and they can only move through solids, not liquids. Because S waves are transverse waves, they shake the ground back and forth, perpendicular to the direction the wave is moving. Surface waves have a lower frequency than either kind of body wave, and they reach the seismograph last. They move the ground in all directions and are responsible for most of the damage caused by earthquakes. Discovering Earth's liquid outer core. By monitoring arrival times of seismic waves throughout the planet, Scientists discovered that S waves do not reach the opposite side of Earth after an earthquake. They concluded that there must be a liquid outer core. This was an important discovery because the deepest well ever drilled was 12 kilometers. Earth's radius is 6,370 kilometers, so the only way to find out the details of Earth's interior comes from monitoring seismic waves and drawing conclusions. Scientists also concluded that Earth's crust is made of less dense matter than the mantle. P waves travel through solids and liquids. S waves cannot travel through liquids. Measuring an earthquake's energy. A seismograph includes a sensor that detects the ground's motion and a recording system. Most seismographs have 3 separate elements, so they can capture Earth's movement in 3 directions: up, down, north, south, and east, west. A simple seismograph has a frame with a movable arm of some kind. The arm is attached to a pen or other recording device and moves whenever the ground moves. The pen, which is attached to the arm, records the relative motion between itself and the rest of the instrument, which is the motion of the ground. Many modern seismographs use electronics to measure seismic waves. The scientists in Southern California use more than 5,000 highly sensitive seismographs. The surprisingly deep earthquakes they measured were microquakes, having magnitudes of no more than 2 on the moment magnitude scale. This scale goes from 0 to 9+, depending on the amount of energy an earthquake releases. Moment magnitude scale, level 0 to 1, no earthquake activity. Level 1-2, movement only detected by seismograph. Level 2-3, hanging objects may swing. Level 3-4, may break windows, cause small objects to fall. Level 4-5, furniture moves, plaster falls from walls. Level 5-6, severe damage to poorly built structures. Level 6-7, buildings displaced from foundations, cracks in earth. Level 7-8, bridges destroyed, few structures left standing. Level 9 and over, near total destruction. The quakes were so deep that typical seismic sensors closer to the surface didn't detect them at all. Scientists still don't know the implications of these deeper earthquakes. One possibility is that the Newport-Inglewood Fault could produce a larger earthquake than scientists have predicted. Another possibility is that deep earthquakes remain small and isolated, and so wouldn't affect the surface earthquakes. Scientists will continue to research these questions because many people would be affected by a massive earthquake. The Newport-Inglewood Fault runs underneath an area of Southern California where many people live, and scientists have predicted that the fault could produce an earthquake of a magnitude 7.4. An even larger earthquake would cause significantly more damage to the structures on Earth's surface, including the homes, office buildings, roads, and bridges in the area. Questions still to be answered. ASAP's team's research opens up many areas for future research. They focused on a 9 square mile area. It's possible that there is something unique about this region that produces the deep earthquakes, or it might turn out that these deep earthquakes are common. Because scientists had thought earthquakes weren't possible in the mantle, they now want to know what process causes the deep earthquakes to occur. Scientists use seismographs to help them better understand these processes. Scientists cannot predict when an earthquake will happen because earthquakes occur suddenly and with no notice. However, they study seismographs and other data to help them make more accurate predictions. The Newport-Inglewood Fault runs through Newport Beach, shown here. Section 2, Communicating with Light Waves. Listening with light. One morning, a car drove slowly on a side road in Texas. Thousands of kilometers away, a computer screen in England filled with a series of red lines, similar to the jagged lines of a seismograph's readings. The red lines represented ground vibrations made by the sound of the car moving over the surface. The vibration caused by the car in Texas were sent to the computer in England by light signals sent through specially designed tubes called fiber optic cables. Fiber optics transmit light. Fiber optics, also called optical fibers, are long strands of pure glass that are as thin as human hair. They are grouped in bundles called fiber optical cables that transmit light signals from one place to another. To transmit means to pass on. Fiber optic cables work because of how light interacts with different kinds of matter. All light is a form of kinetic energy that travels through space and matter. Light is complex, and there is still much that scientists don't know about it. There are different models of light that scientists use to better understand how light moves and how it interacts with matter. One model describes how light moves in straight line paths called light rays. Whenever you see a narrow beam of light, it is actually a bundle of many parallel light rays. Here's a diagram of a fiber optics cable. A narrow beam of light is a bundle of many parallel light rays. Light waves. Another model is a wave model because in many instances, light behaves in a similar way to seismic, sound, or water waves. A light wave is a pattern of light energy that moves at a constant speed until meeting matter. Light waves are kind of transverse waves because the disturbance coming from the source of light moves perpendicular to the direction of the wave itself. There are different types of light, and the type of light energy depends on the amount of energy in the different waves. Visible light is all of the light waves our eyes can see. Microwaves are used in appliances to heat up your food and in satellites for communication and navigation. X-rays are used at the dentist to capture images of teeth and at the airport to see through bags. Radio waves have the lowest energy. Your radio captures radio waves that are sent out by radio stations. Like mechanical waves, light waves have a wavelength, a frequency, and an amplitude. In a light wave, the amplitude is relative to its intensity, which we see as brightness. A light wave with a higher amplitude will be brighter than a light wave with a lower amplitude. However, unlike mechanical waves such as seismic waves, light waves do not need a medium to travel. Scientists know light waves can travel through a vacuum because the sun's light reaches Earth through the vacuum of space. A vacuum is a space that has no matter in it. In contrast, sound cannot travel through the vacuum of space because there are vast empty regions between matter and space, which means that molecules are too far apart to transmit the energy. How light travels. Light waves travel in a straight line, but their paths can change when they interact with matter. Reflection occurs when light bounces off of an object's surface. This happens when it encounters a substance that acts like a barrier. Refraction occurs when light passes from one medium to another and changes its direction. Unlike reflection, the light moves through the second material when it refracts. However, the direction of the path changes. Absorption refers to the interaction of light energy with matter that results in the energy changing to thermal energy. A wave is absorbed when it hits a substance and causes the molecules of that substance to vibrate and move. This causes energy to be transferred away from the wave because it has been absorbed by the substance. Light and color. An object's color is determined by how the object interacts with light and then reflects or absorbs it. Each color is determined by its specific frequency and wavelength. When visible light hits an object, different frequencies are absorbed and reflected. For example, a strawberry is red because it absorbs all of the frequencies of visible light that shine on it, except for the frequency associated with red. Black objects absorb all wavelengths of light and convert them to thermal energy. In contrast, white objects reflect all wavelengths of light. This is why dark-colored objects warm up faster than light-colored objects. Total internal reflection. Optical fibers transmit light through a process called total internal reflection. Imagine that you're standing in a straight hallway. If you shine a flashlight straight down the hall, The light will travel through the hallway to the other end because light travels in a straight line. Now imagine that the hallway has a curve in it. The light will travel in a straight line until it reaches the wall where the hallway curves. Some of the light will reflect off of the wall, and some will be absorbed by the wall. If you want the majority of the light to travel to the opposite end of the hallway, you could set up a mirror at the curve. Mirrors are highly reflective, so they would reflect the light around the corner. In a hallway with many curves, you could line the walls with mirrors to reflect the light all the way to the other end of the hallway. Reflecting light. This is essentially how fiber optic cables work. Each optical fiber has a core, which is like the hallway. It is a thin strand of glass where the light travels. The glass is almost perfectly transparent, which allows light to pass through. The core is surrounded by a highly reflective material called a cladding, which functions in a similar way to the mirrors on the wall. The cladding doesn't absorb any light. Instead, it constantly reflects light away from it. As long as the light strikes the cladding at or above a certain angle, it will result in total internal reflection, where the light is continually reflected back. This is how the light is transmitted to the other end of the optical fiber. Optical fibers transmit light through total internal reflection. Fiber optics communication. Fiber optic cables are commonly used to transmit information in communication systems. A communication system is a group of interacting components that function together to transmit or exchange information between people and equipment. In a fiber optic communication system, information is sent digitally through the cables. This means the information is translated into a numerical value, most often ones and zeros. Different patterns of light wave pulses represent different combinations of ones and zeros. Digital technology is different from analog technology because in analog technology, the information is recorded or used in its original form. A transmitter at one end of the fiber optic cable sends the information digitally. A receiver on the other end picks up the information. The digital information is translated back into its original form, such as sound or light. Fiber optic cables are commonly used in telephone communications. Think back to the computer screen in England filled with a series of red lines when the truck moved over the ground in Texas. That computer screen was a receiver in a communication system that used a fiber optic cable. Pulses of laser light were sent through the cable. When the ground vibrated, it caused extremely small vibrations in the cable. These vibrations caused small changes in how the light moved through the cable. The company that owns the computer screen has designed a special signal processing technique to analyze what the sounds are likely to be, such as a truck, a person walking, or the wind. The left diagram shows an analog signal. The right diagram is a digital signal. Fiber optic cables are going into the ground. Analog versus digital communications. Digital signals are more reliable than analog. This is because the recording does not become less precise over time. As long as the numbers can be read, you will always get exactly the same wave. Because of this, fiber optic communication systems most commonly use digital signals. Think about someone speaking into a telephone. Their voice produces an analog signal in the form of a sound wave. That sound wave enters the telephone, where it is converted to digital pulses of light. This signal is made up of pulses of ones and zeros. These pulses then move through the optical fiber to the receiver, where they are changed back into an analog signal in the form of sound waves that the person at the other end can hear. As the signal travels, it picks up a lot of noise. This is called interference. However, because the sound wave was broken down into discrete numbers, the converter can easily convert the sound wave back to the same pattern as the original signal. In contrast, if the system used just analog signals, it would be difficult to separate out the interference because there are many possible frequencies and amplitudes the wave could have. The end result is a representation of the original signal. This can result in information being lost or garbled when it comes through. Digital calls are also more secure because the digital code encrypts the conversation, so outside listeners cannot follow what is being said. Kinds of communication systems. There are many kinds of communication systems that transmit information. When you use GPS on your phone, you are using a communication system that transmits information about your location through a kind of light wave called a microwave. When you listen to the radio, you are using a communication system that transmits sounds through radio waves. I learned a lot reading Waves and Information Transfer, and I hope that you did too. I'll see you tomorrow with the next one. Bye!